The question is, what is effective stress principle as applied to soil? The effective stress principle in soil is also called Tesagi's effective stress principle. Tesagi is the father of soil mechanics who came up with this idea of effective stresses in soil. Let's start with some basics on stresses. Let me take a very simple system first, a tank full of water. Let me consider point A, which is at a depth of y. Let me draw a little rectangular element around it and look at the stresses acting on its sides. Since water is not flowing, what we have is a hydrostatic water, right? From the basic fluid mechanics, we learn two things. Number one, the stresses are acting normal to these sides. Number two, the vertical stress equals the horizontal stress. This is what we call the hydrostatic water pressure. And also note that there are no shear stresses on the sides, and these stresses are compressive. Its magnitude is given by this equation, and from this equation we see that the water pressure is proportional to y, the depth of point A. If I were to sketch its variation with depth, it looks something like this. In other words, the water pressure varies linearly with depth. The constant of proportionality here is the density of water. Now let's consider a second system where we take this water tank and sprinkle some clay particles in there. So now what we have is a clay water suspension. As far as the stresses are concerned, this suspension system behaves exactly the same as this system right here from a fundamental point of view, in that number one, the stresses in the vertical and the horizontal directions are the same. Number two, they act normal to the sides. There are no shear stresses on the sides of this element. So basically it behaves like a fluid. There's only one difference though, which is now you have to use the density of the suspension instead of the density of water. And obviously the density of suspension is going to be a little greater than the density of water because we now have some clay particles in there. We know that the clay particles have a specific gravity of about 2.7 if you recall from previous chapters, and therefore the combination of water and the clay is going to be a little heavier than water. My third system is real soil. At this point, let's consider saturated soil. I'll come back to unsaturated soil a little later. So what's the difference between this system and this system? Well, in a real soil, the particles are packed and they are in contact with each other. The pores between the particles are filled with water. So what happened to the stresses? So it turns out that the vertical stress is still given by a similar equation. Remember we defined a density measure called saturated density? Well, the constant of proportionality in this equation has to be that, gamma sat. Because this represents the total weight of the material, total weight of the soil, which consists of both the solid particles and water in the pores. What about the horizontal stress? Well, it's a different story. This is where we have to dig into the basics a little bit more. So what I like to do is to section this soil sample horizontally from C to D and see what's going on there in terms of stresses and forces. It's a little easier to visualize the soil particles in the form of sand particles because the sand particles are kind of round and bulky, right? So let's assume that this soil has sand particles in there. So in this picture right here, I have drawn the sand particles to an exaggerated scale so that we can look at what is going on in between the sand particle. When I section it from C to D, I want to run this green line through particle-to-particle contacts whenever possible. So here is a contact. There's a contact between this particle and this particle, and the green line kind of goes through that contact point. And similarly, there is a contact here, there's a contact here, there's a contact there, right? In between the contact points, of course, the green line is running through water. After sectioning from C to D, I want to take this top part, ABCD, and draw it separately and complete the free body diagram. On the top surface from A to B, we have the atmospheric pressure, and I'm going to assume that to be 0 for now. And from C to D, we have two types of forces. There is a force between grains, right? And this type of force is called the intergranular force, and I mark that as F sub I. And in between the contact points, there is water, and let's call the force carried by water as F sub W. So basically, we have identified two types of forces. The forces carried by the soil grains themselves, and the forces carried by water. This type of microanalysis is very good for developing a fundamental understanding of the kind of forces we have there, but it's not very useful for practical analysis. For the purpose of practical analysis, we will define two other quantities, capital Fi, capital Fw. Capital Fi is basically the sum of the vertical components of all the intergranular forces, and capital Fw is sum of all the vertical component of the forces carried by water. So here is a macro level free body diagram showing these forces. So to complete this free body diagram, we also need to mark the weight of the material in this part of the soil, A, B, C, D. And of course, the material consists of both solid particles and water. Let us now define stresses corresponding to these forces simply by dividing them by the cross-sectional area of the section from C to D. Sigma V, defined as the total force divided by the cross-sectional area, is called the total vertical stress. Sigma V prime, defined as the intergranular force divided by the cross-sectional area, is called the effective vertical stress. U, defined as the total water force divided by the cross-sectional area, is called the pore water pressure. Of course, F equals Fi plus Fw. From that, it follows sigma V equals sigma V prime U, and this is what is called Tesagi's effective stress principle. Now, by writing down a vertical force equilibrium equation for this free body diagram and simplifying the equation, we get this equation right here. Sigma V equals gamma set times Y, and remember that's what I marked over here, right? As long as the pores are connected, which is true in saturated soil, the pore water pressure is still given by the same equation that we had earlier for the system consisting only of water. So utilizing these expressions, we now have a way of calculating sigma V prime. So sigma V prime simplifies to this, gamma prime times Y. If you recall, gamma prime is the buoyant density. Now let's talk about the stresses in the horizontal direction. So it turns out there is a relationship between the effective horizontal stress and the effective vertical stress like this, where the constant K naught is called the coefficient of earth pressure at rest. So this is just an experimental fact. We know the water pressure is the same in any direction. So if we have to find the total horizontal stress, all we have to do is to take this effective stress and add the pore water pressure to it. We'll get sigma H. So here is that equation. So to summarize what we did so far, here is Tesagi's effective stress principle. Sigma equals sigma prime plus U. Sigma is the total normal stress, U is the pore water pressure, and sigma prime is the effective normal stress. And this is a fairly general equation. Sigma here can be the normal stress on any plane. It could be the normal stress on the horizontal plane, and it could be the normal stress on the vertical plane. Also note that the shear stresses are not affected by pore water pressure. In other words, the total shear stress is the same as the effective shear stress. So in the earlier slide, we used a container filled with a saturated soil, like shown over here, in order to develop the understanding of what an effective stress is, right? So this is a special application. A couple of things to note here. Number one, we have a horizontal surface to this container full of soil. And number two, this container is filled with a homogeneous soil. Number three is fully saturated, right? For this special case, we found that sigma V, which is the total vertical stress, total normal vertical stress at a depth y, is simply given by gamma SAT times y, where gamma sat is the saturated total density of the total unit weight of the soil. U is the pore water pressure at a depth y, and that is given by gamma W times y. Sigma V prime, which is the effective stress at that point, is simply given by sigma V minus U. And that works out to be gamma prime times y, where gamma prime is the buoyant density of the soil or submerged density of the soil. If we are interested in calculating the horizontal normal stress at that point, this is what we need to do. We need to first calculate the horizontal effective stress, which seems to be linked to sigma V prime through this equation, where K naught is the coefficient of earth pressure. Most of the time, this K naught is the coefficient of earth pressure at rest, okay? And it has a certain value. It's a property of the soil. And then you calculate the total horizontal stress simply by this equation, again applying the Tesagi's effective stress principle for this stress component. Sigma h, the total horizontal stress, simply equals sigma h prime plus U, the pore water pressure, right? Once again, for this special situation, utilizing the equations we already got here, this boils down to this. Sigma h equal K naught times sigma V prime plus gamma W times y. Now keep in mind that this is a special situation. In general, pore pressure could be negative, and this happens when you have capillary pressure in soil. Out there in the field, even if you consider a horizontal deposit of soil, the soil doesn't have to be a homogeneous soil. It typically is layered. So we'll deal with these real situations in other videos.